Good evening, everyone. Welcome to the second live interaction session for the course Waste to Energy Conversion. So, let's just wait for a few minutes for others to join before we begin our session for today. So, let's start our session for today. Let me just share my screen. And so, let me introduce myself again. So, welcome everyone for the second live interaction session for the course Waste to Energy Conversion. This course is offered by Professor Prasenjit Mondal from the Department of Chemical Engineering, IIT Roorkee, under the NPTEL SWAYAM program. Myself, Pratyumnan, a PhD research scholar from the Department of Chemical Engineering, IIT Guwahati, Assam. I am one of the course team member. I will be conducting the live interaction session for this course for this particular Jan to May 2026 semester. So we are in the live interaction session 2. So in the last live interaction session, I hope all of you remember that we actually discussed on the basics of waste material as such. We discussed about what is a waste, and we discussed about the definition of the waste material, and then we discussed on the concept of why we need to actually reduce waste, the sustainability perspective of waste management, and then we went on towards classification of the waste material, such as hazardous waste, non-hazardous waste. Then we discussed about the four different properties which actually classify a waste material as hazardous or non-hazardous. So if you are able to recollect, that is toxicity, corrosivity, reactivity, and one more is there. Anyone? There are four properties that qualify a waste material as a toxic waste material. So one is corrosivity, another one is toxicity, another one is reactivity. Apart from that, it's ignitability. So after this particular class, yeah, ignitability, as someone rightly said now. So after after this particular classification, then we try to classify this waste material based on their source. So we classified them as municipal, agro, and industrial. And after that, we classified them based on their biodegradability and based on their usability as organics, inerts, and recyclables. We also discussed why inerts are not a preferable one in case of a waste material. So material with a high amount of inert content will have a lower heating value, which is not something that is suitable when we deal with the perspective of energy generation from the waste materials. Then we also classify the waste as solid waste, liquid waste, and gaseous waste, and discussed about what parameters we need to look for while using them for the energy generation. Once that was done, then we went towards understanding the physical and the chemical properties of the waste. So in the physical properties, we discussed about, if you remember, we discussed about particle size, morphology, density. Then we discussed about concepts like moisture content, hydraulic conductivity, and we define each of these parameters and understood about how they will affect your energy, how it will affect the properties of the waste material, which in turn will have an effect over the energy generation process. After this, we went on towards the chemical analysis, or you can say the chemical properties of the waste material, which was classified in terms of two different varieties. One was the proximate analysis, and another one was the ultimate analysis. In case of proximate analysis, we will be able to find out, if you are able to recollect, percentage of moisture, the fixed carbon percentage, the volatile matter, and the percentage of ash. Whereas in case of the ultimate analysis, we will be able to determine the elemental composition of the waste material. So for that, we use different kinds of techniques, and one among them, and the easiest way to evaluate the elemental percentage composition is using a CHNSO analyzer. So yeah, so I remember asking most of you, I mean, all of you who were there in the previous live interaction session, to go through the mechanism of the CHNS analyzer. I hope you had time to look through it. In case if not, then please have a look at it on on the working principle of CHNS analyzer, and how it works, and what are the process parameters that are required for them. So once we finish the chemical analysis process, then in order to understand, in order to obtain the heating values, we discussed about the concept of bomb calorimeter. So that is quite important. So we discussed on how a bomb calorimeter is used, the working behind the bomb calorimeter, and then we also discussed about the working principle. So, anyone who knows what is the principle for a bomb calorimeter? Bomb calorimeter principle, working principle. So it is nothing but the heat that is generated by the waste material, or the heat generated through the combustion, is equal to the heat gained by the bomb and the water that is surrounding the calorimeter. So sorry, and the water that is surrounding the bomb. So I will show that here. So the heat that is generated during the combustion is equal to the heat gained by the bomb and the water. So we discussed about this working principle. Just a second. So once this was done, um, let's, okay, just a second. I will. So till this we covered in the last live interaction session, and of course in case of the physical property we went in depth in understanding each of them, so that I am not going, that is for you to go through. So the previous session's recording is already uploaded, so you're welcome to go and watch it through the YouTube channel. So in today's live interaction session, our focus will be on incineration and gasification of the waste materials. So in the last session, we discussed that for generating the energy through the waste material, there are totally three different ways. One is your thermochemical conversion, another one is your biological conversion, and another one is the chemical conversion. So this incineration is typically a process of thermal conversion routes. So the very first process of waste to energy conversion that we will be focusing in this course is the thermal conversion routes. So typically the thermal conversion routes are divided into three different categories. One is the incineration, the second one is the gasification, and then the third one is the pyrolysis. So incineration and combustion, you can often use them as synonyms, so they both actually represent the similar thing. So these two words often from now on we may use it alternatively. So please have it in mind that both incineration and combustion represents the same. So the classification of a particular conversion of a particular thermal conversion route as combustion, gasification, or pyrolysis typically determined by the oxidant to the fuel ratio. So if you see in the table, I hope this table is visible to all of you. So if you see, in case of the different type of conversion process, the value of R, that is nothing but it's the oxidant to the fuel ratio, or you can say the O2 to the solid waste material ratio, actually varies. So if you do this particular combustion process at but at conditions where excess of air is used, then we call it as combustion. If the burning of the waste material is is processed under controlled oxygen environment, where the value of R is between 0.68 to 2.5, then we call the process as gasification. And if the amount of oxygen is much less in compared to that of the solid fuel, then we call that process as pyrolysis. So depending upon the amount of oxygen to the fuel ratio, or you can say the waste material ratio, the thermal conversion routes are classified into three different forms. So in case of combustion, excess supply of oxygen is required. In case of gasification, a limited, or you can say a controlled supply of oxygen or air is used. In case of pyrolysis, a limited supply of oxygen is used. So one thing that is important to note here is you cannot do this any of this process in the absence of oxygen, because for burning process to take place, oxygen is a mandatory requirement. So that is the reason in case of the pyrolysis process we say that we burn the waste material in a limited supply of air, not as in absence of air. So kindly make a note of this point, because often we say that uh, pyrolysis is a process where we actually do the burning in the absence of oxygen. So kindly make a note of that. Now coming to the topic, or what we are particularly interested in this week is nothing but it is the incineration. So in case of the incineration or the combustion process, we use excess supply of oxygen compared to your solid waste material. So the combustion of the waste typically generates gases and heat. So the gas could be, so waste plus air, or you can say oxygen, gives gases plus heat. And these gases could be in the form of CO2, H2O, NOx, and SOx. So different forms of sulfur oxides. It can be SO2 or it can be SO3. Similarly for NO also it can be NO2. So since different form of oxides of sulfur and nitrogen can be generated through this combustion process, I have represented it as NOx and SOx. So these are the gases that can be typically generated through the incineration process. And apart from that, you also will have ash content by burning the waste material. So one of the major advantages of using incineration process is that the gases, so one particular way is that you are able to reduce the waste material. So the waste material that is going to get deposited in the environment is going to be minimized. So that is something like more of a sustainable perspective, or you can say a perspective for a sustainable environment. And second thing what you happen to get is the heat that gets generated through the process. So as you know, this combustion is a highly exothermic reaction. So a lot of heat gets generated. That heat that gets generated can be harnessed. It can be harnessed for various applications. The heat can be directly used for thermal applications, or the heat can also be used in gas turbines, which will ultimately lead to the production of electricity, or the heat could also be used to boil water, which can form steam and then can be used in the steam turbine to generate electricity. So typically the heat that gets generated out of this particular combustion is used either for thermal application or is converted into electrical energy. So by doing this process we have two advantages, and this is something that we discussed in the last class also. Burning of the waste minimizes the waste that gets generated in the environment, at the same time leads to the production of energy. That energy that gets produced is harnessed for thermal application or is converted to electrical energy depending upon the need of the situation. So for a successful combustion process to take place, there are totally three T's are actually required. So without these, incineration process will not be effective, or you can say incineration process or combustion process will not take place. So anyone who knows these three performance factors, also known as three T's, I mean, these are the external factors that is required for the combustion to process to take place. Apart from that, there are also other multiple factors as it is listed below or in the slides if you are able to see. But even if these properties are there, or if it is less or more, unless or until you have these three T's, the combustion process will not be successful. So what are those three T's, or you can say three performance factors that is required for successful incineration to happen? Anyone? uh, Time, temperature and turbulence. Yes, exactly. Temperature, time and turbulence, the three T's that determines how combustion will take place, is nothing but, just a second, it is time, temperature and turbulence. So how these properties will affect, that is something that we are supposed to understand. So with the increase in the temperature, it is obvious that more amount of the waste material will undergo combustion, and that will lead to minimization of the waste and the more amount of the heat that gets generated, which will be useful for increase the energy production. So with the increase in the temperature, the combustion process will be more effective. So as temperature progresses, what actually happens is the waste material undergoes a series of, or you can say a sequence of steps of reactions. So initially when you take the waste material and you heat it, what actually happens is that the moisture content that is present within the waste material is removed. So that is typically called as a drying process. After the drying process happens, the once the temperature keeps increasing beyond the beyond 100 degrees Celsius, what actually happens is initially you will have free moisture. So what is free moisture is nothing but the moisture that is present over the surface of the material. Once that moisture gets removed, if you increase the temperature beyond that, the moisture that is present inside, bound moisture what we call, is removed. If you keep on increasing the temperature in that way, after the removal of the free as well as the bound moisture, you if you increase beyond that, then the volatile species will be removed. So once the volatile species gets removed, what actually happens is pores gets generated. So once the pores gets generated, the oxidant, or you can say the oxygen, can enter inside the pores, and then the combustion process will be more effective. After that, the char starts forming, the lighter hydrocarbons form, which then again reacts with the oxygen to form CO2, H2O, SOx and NOx, depending upon the composition of the waste material that you are taking for study. This CO2 whatever is formed can also react with the carbon matter in the waste to release carbon monoxide. So in order to mitigate that formation of the carbon monoxide, we use a excess quantity of air. So here if you see, you can clearly see in this table. Let me just zoom in. So in case of combustion process, if you see, you often do not have much quantity of carbon dioxide, carbon monoxide or carbon soot particles. Whereas in case if you see in gasification and pyrolysis process, the chances of carbon monoxide getting generated or the carbon monoxide plus soot, that is your solid carbons that is getting generated, will be more. So that gets avoided in case of the combustion process. However, depending upon the how much excess of air you use, there are also a little chances of carbon monoxide getting generated within the combustion process. So this is how as you increase the temperature, the incineration process will happen. The sequence of steps: drying. After drying, you have your removal of volatile species, then you have the char formation, and then the gases gets released and so on. This is with respect to temperature. Then with respect to time, what actually happens is, if you have a waste material, let's say a spherical waste material, as the time progresses, the core of the waste material actually shrinks. So this typically follows a shrinking core model. So as a so I just want to know, how many chemical engineers are there in the audience who have an idea on what is shrinking core model? Anyone who knows what is shrinking core model? Because this is something that we read in reaction engineering, chemical reaction engineering. Oh, I think I received a response. Anyone who exactly knows what is shrinking core model? Okay. Oh, oh, okay. Someone is an electrical engineer. So you can have, so the basic concept is that if you assume the spherical particle, if you assume the waste material as spherical particles, as the time progresses and the combustion process takes place, the core of the waste particle tend to decrease in size. So this decrease in the size is usually modeled, and we name and we give and we give and the name is given as shrinking core model. So if you are interested, then you are always welcome to see how the um, equations are for a shrinking core model. However, this is not as a part of this course. So chemical engineers, we usually read this concept of shrinking core model in reaction engineering. So if anyone is interested, then you are welcome to go through what shrinking core model is. Then after that we have turbulence. So turbulence is nothing but, it's like you try to increase you try to introduce some sort of a turbulence so that you can increase the amount of oxygen that comes in contact with the waste material. So for example, if you have a waste material, and if there is oxygen concentration present around the waste material, by introducing turbulence you can increase the amount of oxygen or O2 or air that comes in contact with the waste material, so that the combustion process will be effective. So without temperature, time and turbulence, a successful combustion process is not possible. You need sufficient temperature, you need to give sufficient time, and also sufficient amount of turbulence is required for a optimum and a successful combustion process to take place, and to so that you can extract increase the amount of heat energy, so that the basically to say in a simpler sense, the energy efficiency of the process can be enhanced. So there are also other multiple factors that affects the combustion process. As such, from the material perspective, if you see particle size, specific gravity, moisture, CHN content, that is very important. It will uh, it will alter your heating values and the ash content. So this is about combustion process. One thing that I would like to mention here is uh, the concept of excess of air. So when I say excess of air, what I typically mean is that how much amount of air, more air is required apart from the stoichiometric quantity of air. So that stoichiometric quantity needs to be present so that the materials can react with the oxygen to form your to form gases. How much amount of more, how much more air is required than the stoichiometric quantity is what you call as an excess air. So excess air is nothing but the excess of air that is required beyond the stoichiometric requirement is what is actually we mean by excess air requirement in these cases. So this is something that you need to keep in mind as well. So coming towards the incinerators, so this incineration process needs to be typically done in some sort of a setup, right? So for that we use two types of setup: fixed bed and fluidized bed. So again, as the name suggests, you have one bed which is fixed and another one which is fluidized. So in case of fixed bed incinerators, the primary mode of heat transfer is through radiation, whereas in case of, so one of the the primary advantage of using a fluidized bed over a fixed bed is that in case of a fluidized bed, the waste particles will be in a continuous motion. The waste particles will be actually fluidized. So the rate of heat and mass transfer in case of a fluidized bed will be much higher compared to that of a fixed bed. So in a fixed bed, what actually happens is this waste material is in the form of a bed, and then the oxygen is supplied, the temperature is increased, and the combustion process takes place. Whereas in case of a fluidized bed, what actually happens is you actually use a separate media which is nothing but the sand particles, and then your solid waste material. So both these particles are fluidized, they are in a continuous motion by, and for this you supply excess of air from inside, so they are in a continuous motion. So due to this continuous motion, what actually happens is they are more prone to undergo collision with one another. Due to this, the rate of heat transfer in case of a fluidized bed will be more compared to that of a fixed bed. So this is something which you need to keep in mind. So if suppose ask the question, which one will be more suitable for the incineration process, is it a fixed bed or a fluidized bed, then the answer is straightforward, it's a fluidized bed. Major reason being is that the solid waste particles in case of a fluidized bed are in a fluidized state, so the rate of heat transfer in case of the fluidized bed will be more, so the process or the combustion process will be more efficient in case of a fluidized bed. So increased energy production is possible in case of a fluidized bed, which ultimately leads to increase the energy efficiency of the combustion process. So again, this fixed bed is classified into two forms. One is your underfeed stalkers and another one is your great firings. So we will discuss those in the form of questions, which we will be going through in a short span of time. Then you have about then you have about the fluidized bed. So as I said, in case of the fluidized bed as well, you have two types of fluidized bed. One is your bubbling fluidized bed and another one is the circulating fluidized bed. So in both these cases, they vary in terms of velocity of the air that is passed through the system. So which one actually has more in, or I will put the question in this way. In which system the velocity of the air is more? Is it in case of a bubbling fluidized bed or a circulating fluidized bed? What do you think? In which system the velocity or the air velocity is more? Air velocity is more in which of the fluidized bed system? Bubbling fluidized bed or circulating? It is circulating fluidized bed. So over there, the velocity of the air is more. So, so yeah, that is totally fine. Apart from that, we just a second once. Do we have anything more? Okay, so this ends the discussion on the concept. So I wanted to keep it in brief. So that is the reason I have tried to complete it within a very short span of time. So again, in case of a fixed bed, we haven't discussed about the different types of fixed bed that we have. So fixed bed is classified into two forms. One is the underfeet stalkers and the other one is the grate firing systems. So in case of, I will not discuss those in detail, but those we will discuss in the form of questions. So I will just write it here. Underfeed. So in case of fixed bed, you have underfeed stalkers, and then you have grate firings. And in grate firings, you have multiple different varieties: reciprocating, rocking, roller, and rotatory kin. So those we will discuss as we move forward. So let's start with our practice problem session. So yes, let me just. So question 1, identify the type of combustion chamber that is used in the following, um, you can say, diagram. So is the combustion chamber, is it great combustion chamber or fixed combustion chamber or fluidized bed combustion chamber? It should be fixed bed combustion chamber. Okay. Anyone? Based on the picture, what type of a combustion chamber is it? Is it a fixed bed or a fluidized bed, or in that fixed bed is it a great firing combustion chamber? Oh, fixed. Okay, one person says it is fixed. Any, so is it fixed bed combustion chamber? What about others? I mean, that just, it's great combustion. Okay, so two different answers. Anyone, anybody else? Oh, I'll just show the. So two of them have told, one of them said it is a great combustion chamber, and another person told us that this is a fixed bed combustion chamber. So which one is right? Any third answers from anyone so that we can. So just think about this. Somebody says it's a parallel or a co-current great combustion chamber. Okay, so they say that it's a great combustion chamber. Just a second, let me just stop sharing the screen once and then share it back again. So this screen is visible, right? Completely, including the question 2. Okay, fine. Because I was having a doubt whether. So with this, I think it will be easier for me to. Is it possible to reduce? Yes. Okay. So yeah, so that's fine. So what will be the answer? Is it great combustion chamber or fixed bed or fluidized bed? Just a let me go back to that same way. Okay, we have someone saying great combustion chamber. Okay. Okay, so this is great. The answer is great combustion chamber. Now, in this one, let me know whether, so in case of the great, so what is actually a great combustion chamber? Or in case of, let us explain what is first underfeed stockers. So in this case, it is nothing but it is very simple. So here, the material actually flows from the bottom of the combustion chamber, or you can say furnace as well. So in case of the grate firings, the main purpose of the grate is actually to hold the waste material inside the incinerator. So that is the main purpose of grate firing. So why we use grate firings? That is typically for making sure that you hold the waste material inside the grate. So once you hold the waste material inside the incinerator for a longer period of time, the combustion is going to be more effective in this case. And since you use grate firings, what actually is one of the additional advantages that the waste material as well as that of the air will be evenly distributed over the grate firings, so that helps in making sure that the combustion process will be more homogeneous, more effective, and the combustion products will be more stable. So main advantage of using grate firings is that the the waste material and the air evenly distributed over evenly distributed over the grate, and that makes combustion effective and combustion and homogeneous. So there will not be any case of heterogeneity, like in one place there will be more combustion, so more so the more combustion will take place, and in some cases less combustion will take place and majority of the waste material will be there. So that kind of heterogeneity within the system will be avoided in case if you use grate firing systems, and the combustion products are stable. So this is about grate firing. So based on this, the question was, so based on this, now tell me, in the grate combustion chamber, we have totally three different types. Let me push this ahead. So one is reciprocating, another one is rocking gate, third one is roller grate, and fourth one is rotatory kin. So among these four, which one of the following corresponds to the or matches with the schematic that is given in question 1? Is it reciprocating grate, roller grate, or rocking grate, or rotatory kin? Two different answers. One answer is roller, one is reciprocating. So one idea that I can give is, look carefully in the bottom of the schematic, the waste combustion of the combustion chamber. Two answers on reciprocating. Okay. Any other answers? So some say it is reciprocating, some says it is roller. Any other answers from anyone? So the clue is, look carefully at the bottom of the combustion chamber and then let me know what is your response. Roller. Okay, so it is roller grate because you have rolls. If you see, so this is roller grate combustion chamber. So the main difference in reciprocating, rocking and roller is, in case of reciprocating you have stairs. So what, how the mechanism, or you can say how it will look is, one particular stair will be fixed, the second stair will be alternating. So due to this, what happens is, so alternating in the sense there will be a motion in the second stage. So because of this, the waste material will actually move forward. In case of roller grates, you have rollers to actually push the waste material, the rolling motion, or you can say the rotatory motion of the rolls helps in pushing the waste material forward. So that's something that is happening here. So that is why I asked people to have a look over the bottom part of the combustion chamber here, or you can say the bottom part of the schematic. So you have rolls and you feed in the waste material. Due to the rolling motion, the waste material actually is pushed forward or it moves forward. So this is a roller grate. Then there is something called the rocking grate. So where you use a rocked grate, and that creates a upward and a forward motion which advances the waste material to move forward. And then the final one that you have is the rotatory kiln. So rotatory kiln is something that is commercially used, widely used, uh, and what it typically looks at, as in, it actually consists of a cylindrical chamber, assume, or imagine a cylindrical chamber which is inclined. So from one end you actually pass the waste material, and this inclined cylindrical chamber is rotating. So due to this rotatory motion, what actually happens is, it is going to, just a second, yeah, so due to which the waste material actually moves down, and you fire that waste material in the other end. So due to this, what happens is, the waste material moves in along one direction, and it gets burnt, and then the gases are released in the other direction. So this is the concept of rotatory kiln, and this is commercially used and widely used in many commercial applications. So again, based on the flow of air and flow of the waste material, the system or the grate firing system can be classified into three different types. One is parallel flow, second one is counter flow, and third one is center flow. So based on the schematic, which particular flow is followed in this combustion chamber? Is it parallel, counter, or center? Parallel, counter, or center flow? Which flow is does this combustion chamber follow? Is it parallel or co-current, you can also say, or is it counter current, or it is center current flow? Look at the way the base material and the air is actually flowing through. Counter current, counter, parallel, parallel. Okay, so I mean there is a multiple response. So this will actually follow a parallel flow or a concurrent flow. So if you see the way the air and the waste material is moving, oh, yeah. So that both of them is in the same direction. So if you see, that's what is actually indicated here. This is actually the flow of air, and then the waste material is also moving. So if you have, so in case of the counter flow, the waste material movement will be along this direction, and then the air will flow in the other direction. So that is counter flow. And in case of the center flow, the airflow will be along the center of the combustion chamber. So in order to say what this combustion chamber typically represent, then it is called great combustion chamber, or you can say a roller great combustion chamber, following a parallel flow of waste material and air. So is it okay, or anything that you would like to discuss here? Is every particular classification okay, or any ambiguity? So now since you know this, let me know what type of combustion chamber is represented in question number 2. If you have any ambiguity related to question 1, you are welcome to let me know. For others, if you are fine, if you are comfortable with the classification that we described right now, based on this classification, identify the type of combustion chamber that you are seeing in question 2. Reciprocating. Oh, we have roller grate and traveling grate or same. I am not able to, Mr. Shivakumar, I do not really get what you actually mean by traveling grate. So we have three types. One is four: reciprocating, roller, rocking, and a rotatory kin. So I am not able to actually get what do you mean by traveling grade. So so if anyone has any doubts on why, because here if you see that airflow is perpendicular, so kindly look at the direction of the airflow based on this arrow. So that is the direction of airflow. So if you see based on that, then the waste material and the airflow is along the same direction. So that is the reason this is a parallel flow. So, okay, if this is parallel flow based on what I described, what about rotatory kin? Does it follow parallel or does it follow counter? Let's discuss question 2, but based on this parallel, counter and center flow, what does this rotatory kin follows? Counter or parallel flow of waste material and air? parallel. I So think about this for roller for rotatory kin. What will be the flow? Is it parallel or is it counter? And then let me know later. So question two: is it reciprocating or is it rocking? It will not be roller because you do not have a roller arrangement. So is it reciprocating or is it roller? I mean, sorry, rocking. Great. Reciprocating. Great. Yes. So this is nothing but this is reciprocating great combustion chamber. But how did you differentiate between those? I mean, why it cannot be um, rocking great combustion chamber? Is there any specific reason to, or I mean, is there any specific identification element that you observed here that you told that this is reciprocating and not rocking? Any arrangement will be different there. Air from the bottom and there are pusher feeders from the waste entry side. So have a look at those arrangements. So here I should have had that differentiating picture here. So this is reciprocating grade. So but have a clear have a clear understanding of the picture on why it is roller, reciprocating and rocking. Probably when I upload this presentation, I will have all the three side by side and then I will justify how what is exactly the difference that separates them in terms of their classification. So, moving to question 3, what is the correct sequence of the biomass based incineration process? This we discussed just now. Is it drying, pyrolysis, reduction, and combustion of volatile and chars? I mean, what is the exact sequence of the incineration process? A, option A. So that's correct. It is drying, pyrolysis, reduction, and the combustion of volatiles and char. So drying, as I said, when you keep increasing the temperature at particular temperature, your free moisture will be removed. Beyond that, your bound moisture will be removed. Beyond which pyrolysis process will take place, leading to the formation of char, and then that combustion of volatile and char also can take place. So this is A. So I think this was quite straightforward. Do we have any questions? Okay, everyone has responded as I as answer. So let's move to the next question. In gasification process, if air is going to be used in place of oxygen, then the produced gas contains high amount of. So let's assume that instead of using pure oxygen, I do not have or I am not available. I do not have the availability of oxygen. So instead of oxygen, I'm going to use air as a medium for my gasification process. Then the produced gas that you get at the end, or you can say even the incineration process, then the produced gas that I'm going to get at the end will have a higher amount of sulfur, hydrogen, nitrogen, or carbon dioxide. C. Okay. Option C. Nitrogen. Nitrogen. Yes. Air has a high quantity of or higher percentage of nitrogen. So if you see any air charts, you will have 79 percentage of nitrogen, and the rest will go for oxygen. Typically speaking, 21 percentage oxygen. There will be a slight percentage of carbon and all the other composition. So, but as such to say, nitrogen percentage will be higher. So due to that, the produced gas at the end will also contain high amount of nitrogen in them. Now come to question 5th. Which of the following is not a type of grate firing combustion system? Fixed grate, moving grate, rotating grates, and vertical grates. Vertical. Oh, there's a doubt, I think. Yes, that is true, Sri Karthik. It will have a high percentage of CO2, but in comparison, so this is relative. So if I use only air, then CO2 will be more. If I use instead of air, if I'm going to use nitrogen, I mean sorry, sorry, instead of oxygen, if I'm going to use air, then also CO2 will be present. But in comparison to the, if you purely use oxygen, the NOx, whatever form of nitrogen oxides that will form will be less. But if you use nitrogen, sorry, if you use air, then that produced gas will have a high percentage of oxides of nitrogen in them. So that is the preliminary difference that I wanted to mention here. I hope that clears your doubt. It's relative, so we are speaking relatively whether what will happen if we use air and what will happen if we use oxygen. Okay, so I hope that clears your doubt. For question 5, it is vertical grades. Okay, that's exactly correct. But apart from that, these two, we are familiar with the rotating grades, we are familiar with vertical grades. But what is fixed grades and moving grades? Or which one do we classify is classified as a fixed grades and moving grade? Rotating we just now went through the question number 1. Vertical grades are, as you all say, it's not going to be a type of a grate firing combustion system. So apart from that, you have two, something so called as fixed, and the other one that is moving. So, but we did not study anything like that. So is it a synonym for some other type of grading systems? Yes, anyone? Reciprocating have fixed and moving grades. Yes, that's true. But then what about rock? In which particular classification what do you say? Can you keep this rocked grades or rocking grades under? Under which classification do the rocking grades come? Is it fixed or is it moving? Rolling and rotating grades are same. So rocked grade, as someone says, it is a fixed grades. Okay. Try to identify. Let's see what it will be towards the end of the session or sometime later. Because if we get a question like this, then we need to know what it would be. Because yes, as someone said, reciprocating can be a fixed grade and a moving grade, because one of your this thing is going to be fixed and the other one is going to be in the alternate motion. But what about rocking grade? Someone has told it's a fixed grade. So try to identify this. Let's see in the next I mean probably towards the end of the session. If you want, you can actually go through the video lectures as well to and try to get an understanding on this. So before that, so this is about the multi-choice question that we have. Mm, mm. Let's start solving problems related to this particular session. So this should be somehow question 6. Ordering has changed. So first let's go through question number 7 before going to question 6. So let me read out the question. Please solve. This is something very similar to what we did in the last live interaction session. This question. So here I asked you to calculate the gross heating value Hg. Now here the question is to calculate the water equivalent of the bomb calorimeter, that is W. So try to solve this problem and let me know what you are getting as answer. Here your HHV is given, and you have your acid titration, that quantity 11.9 ml, amount of par 4 5 C10 nickel chromium fuse wire is also given, the net rise in temperature is given, mass is also given, how much sample that we are going to take under consideration. I will, for your convenience, if you want, let me. You can use this equation, but again you need to change the numbers, so please be careful. Yes, any answers? Oh, answer will be 1646.3. Okay, let me just wait for a few minutes, a minute or two, before I start solving. But please solve the problem, because you are expected to have these kind of questions. And I think your assignment one also has a very similar question where you're supposed to calculate the gross heating value, if I'm not wrong. We need to modify this equation because we are supposed to calculate W. So water equivalent of the bomb calorimeter is W. So all these expressions that is on your right hand side will go to the left hand side. So anyone else? Yeah, Harpreet Kaur, you can go ahead. Please ask your doubt. Scientific calculator, I don't think so. They allow you to use a scientific calculator because, as far as I know, you will have a virtual calculator during the exam. So you can use that, but I don't think they will allow you to carry a physical scientific calculator along with you in the exam hall. So, I mean, if you want to have a better clarity regarding this, then I would advise you to email to the email to NPTEL itself, because they will be more what do you say, they will be the appropriate ones to answer this particular question. But as far as I know, they do not allow. You will have a virtual calculator that will be available on in in your computer screen, and you will be able to use that to do the calculations. But again, it is better for you to ask that. Yeah, so yeah, see, somebody has said we have to use system virtual calculator. Okay. So someone also has told that the answer will be somewhere around 1642.5. Okay. So let's start solving. So based on what I just said, then we have to rephrase this equation. So water equivalent will be equal to m, that is the mass of the sample that you are going to take under consideration. We here it is going to be 1.1651 gram. H, that is nothing but your HHV value, plus E1 plus E2 plus E3 divided by delta T, that is nothing but 4.5 degrees Celsius. So water equivalent of the bomb calorimeter will be equal to mass, that is 1.1651 grams, times HHV, that is 6318, plus E1. What is the value of E1, E2 and E3? E1, E2 and E3 values. E1 is 11.9. What is the unit for this? 11.9 m, it is written 11.9 ml. So E1 is actually a correction factor, if you remember. So last time if you see here, yes, where is the exact yeah, so the titrate volume for the titrate for the calorimeter washing using sodium carbonate, the volume that is required is 24.2 ml, and then the normality of the sodium carbonate that you are going to use is 0.0709 normal. Now here, last time when I also mentioned this, or when I was solving this, I expected someone to actually let me know that I am doing a mathematical error. There is an error within this problem if you look closely. So the E1 has a unit of 24.2 ml, but whereas the other quantity is in terms of calories. So how can you add two non-identical or non-identical dimensional quantities together? So there is a mistake with respect to calculating the correction factor here also, right? Let me make this make it bigger. Yeah. So what is the mistake here, and How you are saying this as 11.9? Is it 11.9 ml or does it have any other units? Or are we missing something from our side? Oh, there was some response. Okay. So you need to actually multiply this with the 1. In case if you see the correction factors, this should be multiplied with 1 calorie per ml. So that actually makes up 24.2. Similarly, here also 11.9 ml times 1 calorie per ml. So that totally makes it as 11.9 plus E2 is some, as someone said, E2 value is 0. Why? E3 is fine, 2.3 times the length of the par 45 C10 nickel chromium fuse wire that is used, that is going to be 8. But why is E2 0? This divided by delta T, that is 4.5. So that there is nothing much. Why is E2 0? Or I will put the plus sign here. So as someone said, E2 is 0. Why is it 0? Percentage of sulfur in the system is 0. So in the question we didn't, the sample that we are going to take is a benzoic acid sample, which is not actually going to have any sulfur content present in them. So the E2 correction factor is for the percentage of sulfur that is present within the material. So here since sulfur is not present, it is going to be 0. So if you calculate this, then let me use a calculator. It is 1.1651 times 6318 plus 11.9 plus 2.3 times 8 is 18.4. 7391.4018 by 4.5. 1642.53, and the units are calorie per Celsius. Better to keep calorie per Celsius. So I hope the two answers that I received had similar values. So I hope there is no doubt with respect to the calculation calorie per Celsius. So that's fine. Just a second. Okay. So, is there anything that you were not able to have an understanding? And this correction factor values, it typically depends. In case if you for specifically for the value of E3, if the wire that you are going to use is going to be some other materials, then the correction factors that you are supposed to use for calculating will be different. So please be careful when you use this particular when you go for calculating the value of E3, anything that is still you are not able to get in the question. I think we have solved two problems with the similar, two problems are solved, similar problems. Just the parameters that you are supposed to evaluate will be different. Again, variation in the questions can be introduced. I can give all the parameters and ask you to identify the mass of the sample that was used, or probably give all the values and ask you to find the correction factors, let's say E3, and then ask you how much amount of nickel or how much amount of the wire was consumed or is left out. And then again, though, it's just playing with the equation, the mathematics part of it. But I hope there is nothing related to the logic. However, in case if you have, you're welcome to let me know. So if you do not have, then let's proceed to question number 6. Or if you have anything, please let me know. For those who are comfortable with that particular question, kindly see question number 6. COD analysis, chemical oxygen demand of a wastewater sample is carried out through chemical method using normal by 5, that is 1 normal by 5.2 normal potassium dichromate solution as a reducing agent K2Cr2O7. Excess dichromate is titrated against a ferrous ammonium sulfate. 300 ml of wastewater sample is used. The titer values of ferrous ammonium sulfates are 55 and 81 ml of the original sample and blank sample. Determine the COD of the sample. Assume that there is no interfering element in the sample. First of all, last class also we discussed, many of you were able to say what is the value, what do you actually, the full form of BOD, COD and TOC. But what does exactly COD represents for? Yes. What does typically COD represents for? Try to identify, because those kind of terms will be important. We will talk about those things in detail when we deal with the biological conversions. So for this problem, how to solve, let me just give you the equation so that it will be useful. I mean, if anyone does not know, then it will be. So COD in milligram per liter is going to be equal to VB minus V naught times 8,000 times normality by volume of the sample. VB and V naught. VB is nothing but volume of blank sample, and VO is volume of original sample. And the volume of this volume is the volume of wastewater, volume of wastewater sample. Based on this, calculate COD in mg per liter. I think once I gave the equation, now it's about mathematics. So just substitute the values and then calculate the value of COD. Yes, answers. Oh, they were answers. Oh, we had answers. Oh, sorry. Sri Karthik, I don't think that value difference is too much. So for the previous question, I think you got 1646.3. Kindly check with maybe minor calculation mistakes here and there, but I don't think that's a big difference. So just check once and then let me know. Rest it is they have told for the second one as 138.67. Okay, so let's calculate. 81 minus 55 times normality is going to be zero point 0.2 times sorry, by 300. Is that correct? So that is going to be 81 minus 55 is 26 times zero point 0.2, that is 5.2 by or times 8,000 divided by 300. 138.67 milligram per liter. Now express the same COD in terms of ppm. Before that, I'll just express chemical oxygen demand CO2 milligram per liter in terms of ppm. This is in milligram per liter, but I want the unit conversion to ppm. So because for in 1 liter 138.67 milligrams is very less. So if you are able to express this in ppm, then it would be very good. Usually smaller quantities we use represent them in ppm, or even if it is further smaller, then we usually go for units like ppb, parts per billion. So do I have answers? Oh. 1 mg per liter is 1 ppm. So that is nothing but 138.67 ppm is the COD um, of the sample. So let me just make a mention here. 1 ppm is equal to 1 milligram per liter. So please remember this, because sometimes you never know that you may not be able to answer a question just because you actually do not know the unit conversion. So there may be questions in such a way that the trick will be within the units. So please remember this: 1 ppm and 1 mg is equal to 1 mg per liter. So anything that you would like to discuss in this question, or shall we proceed further? We have actually quite a few of them. Three of them left out, but let's try to complete at least one or two. Anything in this? Okay. If nothing, then shall we progress towards? Let me just check. Okay. Let's move towards question number 9. Or just a second. Okay, let's go to question number 9. MSW, a municipal solid waste, has the following composition on mass basis. You have carbon 42.22%, hydrogen as 3.56%, oxygen as 28%, nitrogen as 0.50%, sulfur as 0.20%, Cl as 0.75 percentage, moisture 20%, and ash 4.77. So if you add them up, you should get around 100 percentage. If not exactly 100, then somewhere closer to that. Assume that the average molecular weight of ash is 72. Determine the molecular formula of the municipal solid waste, and if this waste is incinerated in a fixed bed incinerator, what will be the composition of the flue gas if 30 percentage of excess of air is supplied? Second, if the ash of the above sample contains 0.2% K2O and 0.6% Na2O respectively, determine the waste which will form slag in the furnace. So let's talk about the part A. Part B, let's see whether we have time, because we have to introduce the concept of slagging in the furnace. So let's first try to solve the first part of question number 9. How to go about this? The approach. So we have around 10 to 15 minutes left. So let's see how much we can complete. But what is the approach on how to solve this problem? This is a very big one, so it will take time to solve. So, oh, someone has said something. Oh yeah, Debendra Kumar, how we get the normality? It is given. So n by 5, what they typically mean is 1 normal divided by 5. So 1 by 5, that is zero point 0.2 normal. So again, I think, so yeah, that query has been clarified. So so thank you for your response, Lakshmi ma'am. So yeah, what about this question? Meanwhile, you solve this problem. Last week, I asked this particular question. If you see in the upload, also, I have left this question blank. I wanted all of them to try out this particular question. Did anyone come up with an answer for question number 8 of week 1? It's a very simple question, not a very tough one. So, in case if anyone had tried out, let me know. Meanwhile, please see through this question. Please let me know what's the approach you are going to use for question number 9, because it's, as I said, it's a very big question. So if you tell me the approach, then we can start solving simultaneously. Anyone the approach? So the very first, you can say, step is, you, since these composition is given on mass basis, so you have to take a basis. So we assume our basis as 100 grams. Again, it totally depends on you. You can have the basis as even 1 gram. For simplicity in calculation, I am going to use it as 100. So using the basis, mass basis is your choice. You can use 1, 20, 100, 1000. Oh, I think you, Sai Karthik, Sri Karthik, I think you copied and pasted, so it has come out to be, it is not clear. So, anyway, that's fine. I hope you have followed the same procedure, but in case if you have anything different, then let me know. So, based on this, by considering basis as 100, your carbon percentage is going to be 42.22 grams. Um, Hydrogen is going to be 3.56 grams. Oxygen is going to be 28 grams. Nitrogen is going to be zero point 0.5 grams. Sulfur is going to be zero point 0.2 grams. Chlorine is going to be 0.75 grams. And moisture is going to be 20. Moisture is nothing but H2O. And your ash is going to be 72 grams. Now, with respect to this, we are supposed to calculate the mole moles. And once we come to know or we get to know the moles, we are supposed to calculate the molecular formula using mole fractions. So let's see. So for moles, we have to divide each of the element their given weight by their molecular weight. So carbon is 42.22 by 12, hydrogen is going to be 3.56 by 1, oxygen is going to be 28 by 16, nitrogen is going to be zero point 0.5 by 14, sulfur is going to be zero point 0.2 by 32, chlorine is going to be 0.75 by 35.5, H2O is going to be 20 by 18, and ash is going to be, sorry, ash, it should be 4.77 here, and here it will be 4.77 by 72. So now with respect to this, we are supposed to calculate the number of moles. Okay, somebody has given the moles for us. So let me just quickly check that calculation. 3.5 for carbon, yes. And 3.56 for hydrogen. For oxygen, it would be 28 by 16, which is 1.75. For nitrogen, it's going to be zero point 0.5 by 14, that is how much? 0.03. For sulfur, it is going to be zero point 0.2 by 32, that is going to be 0.00625. For chlorine, it's going to be zero point 0.7 by 0.75 by 35.5, that is 0.021. 20 by 18 is 10 by 9, so that will be 1.11. And ash is going to be 4.77 by 72, that is 0.066625. So is it correct or oh, yeah, everything is matching. Now, after this, what are we supposed to do? What are we supposed? We have calculated the moles. After calculating the moles, yes, anyone? What's the total number of moles? What am I supposed to do after this? Or how do I write the molecular formula? So molecular formula will be C 3.5, H 3.56, O 1.75, nitrogen is 0.03, and sulfur is 0.00625, chlorine is 0.021, H2O is 1.11, and ash is 0.06625. So this is the molecular formula for the MSW. Now you are going to make this react with the 30 percentage of excess air, and then you are going to check what will be the percentage, the composition of the flue gas. So in the flue gas you are going to get CO2, H2O, NO2, SO2. Then you will have, what else you will have apart from these two? Cl2, because you have chlorine. Then ash will also be there. Then N2 will also be there. Some amount of nitrogen will come out as N2. And since you have used excess of air, you will get O2 also. Sorry. So this will be the flue gas composition. So I mean, what constituents will be there in the flue gas? These are the constituents if someone asks. Now for this we need to calculate how much of each will be produced, or how much of each of them will be present in the flue gas if 30 percentage of the excess of air is supplied to combust or incinerate the municipal solid waste with a particular molecular formula. So please do this, and let's see the answer in the next class. So I want the answer for question number 8 as well. So if you have done, then please let me know, or if you did not have time, in the last week, kindly do this question in this week, because for the first 3 to 4 weeks we will discuss with thermal conversion routes, after which we may not be having time to revisit these concepts once again. So then it may not, then it will be quite difficult for me to for us to actually go to this particular question and then discuss them within this 2 hours of time that we get. So please solve this, and then if you have any doubts, or and then please let me know the answer in the next class. Along with that, solve the part A, the composition of the flue gas. Someone has just posted this. Let's see in the next class what will be the composition. So I'll not be posting answer for this question. So please solve it, and then we will take up from here in the next live interaction session. So other than this, we do have two more. It's okay, we will take up this question in the next live interaction session. So till the time we are there dealing with the thermal conversion routes, we can always go back and forth. The problem arises once we close the thermal conversion routes and move towards the other forms of waste to energy conversion paths. So these two questions we will take it up in the next live interaction session. So for this week, the task will be to complete part A and the question number 8 of week 1 live interaction session. So I kindly request everyone to do these two questions in the free time that you get over the week, so that it will be beneficial for everyone, and we can discuss that in the next session on the coming Sunday, next Sunday. So, if you have any doubts, you are welcome to let me know, or else we can close the session for today. Let me just stop sharing the screen. Yeah. In case if you have any doubts, or if you want to let me know anything, then you are welcome to post your comments in the chat box or unmute yourself. So even if you have any feedbacks with respect to how this live interaction session is progressing, you're also welcome to let me know now, or through my email ID, which will be available along with the slides that I will upload. So in case if you have any feedback related to the session, like the pace at which we are going is too slow, or is going too fast, or it's fine with you, or do you want to solve more problems and then reduce the time that we dedicate for the concept revision, then please let me know, so that we can reiterate, so that I can restructure the way I'm taking the session and reiterate it, and so that it will be beneficial for everyone. In case if you have any comments related to regarding that, then let me know. So if you have no comments, then yeah, so thank you all for joining today's live interaction session. Our next live interaction session will be on 8th February, same Sunday, 5 to 7 p.m. I hope to see you all there. So I take this as an opportunity to thank Professor Prasenjit Mondal sir, as well as the NPTEL team, for providing me this opportunity to interact with you all. on this Saturday, on this Sunday afternoon. So hope to see you all in the next live interaction session. So till then, thank you and bye.